problem where we're looking at finding the pH of a buffer solution. So they give us some description of this solution that has the weak acid and its weak base. The weak acid is at a 0.075 molarity concentration. And the conjugate base, this minus that proton, the conjugate base, has a 0.030 molarity. And again, this is about the simplest type of problem you can be faced with where you're asked to find the pH of a buffer. Remember, they can start you off with the liters that was titrated, or the liters amount of the weak acid that was added to some amount of the weak base. Because in lab, really, you're not going to have these solutions preset. You tend to make buffers by adding two solutions together, having a volume of one and a volume of the other. But they give us sort of the final picture. This is now one volume. They've been added together and they have these particular molarities. So how can we find the pH? Well, again, there's kind of two parts. You have to go through your ICE table and then the law of mass action. So the ICE table, let's do that first, ICE, and we're going to put our reaction that we have with water. So we have a Ka given. That usually tells you what to use as your reaction that you're going to put to the ICE table. Ka means it's the equilibrium constant for an acid. So we want to start off with the acid HNO2 reacting with just water, because that's what you're putting this solution in. There's a lot of water. And we have the conjugate. Now I'm not going to show the sodium. I'm just going to have the conjugate base of the weak acid. And we know then that this acid proton would combine with water to make hydronium ion. And this is what the Ka is for this reaction. So we need to show that reaction in our ICE table. All right, so initial concentration of HNO2 is 0.075. We don't worry about the water, there's an excess of it, and it stays at a certain concentration. And we say the nitroso ion is 0.03. Nitrous, not the nitrate, it's NO2, so it's nitrous ion, or it's not nitrate, NO3, but it's just short of that. It's a different type. And this would be, we'll say, 0. Now, of course, again, this is not exactly, it's not exactly 0, but we're saying generated from this acid, there's a 0 amount. So the direction of this reaction would certainly be to the right. So we'd say minus X for our change. We can disregard the water. We say plus X and plus X. So our equilibrium will be just, in all intents and purposes, just 0.075, because this is so small, X is therefore small. So 0.075, if X is small, this is essentially 0.03, and we have X. So now we can take this into our law of mass action. The 4.5 times 10 to the minus fifth is equal to products. So we'll say 0.03 times X over 0.075. Now again, I need to make sure I'm using molarities here. Yeah, that was a molarity, not moles. This was molarity. So now we just do the math, and we'll be able to solve for X. So I'm going to times this by the 0.075. And I'm going to divide it by 0.03. And I'm going to get, as a concentration, sorry, our dogs are barking, we're going to get 1.125 times 10 to the minus 4. Now it's not asking for a concentration of hydronium ion, it's asking for pH. So I'm just going to take the negative log of this now, because that is what pH is the negative log of hydronium ion concentration. So the pH would be equal to the negative log of this. So it would be 3.94, we'll say 9, would be our final pH. So I guess some thoughts on this. Does it make sense? Well, we do have a little bit higher concentration of the acid in this buffer than we do the base. So that tends to maybe argue why this would be a little bit lower than 5 or 4. So make sure you do your math just to make sure, but that seems to make sense. We're a little bit lower because we have more acid than we do the base. And that's how we find the pH of a buffer solution.